Hello and welcome back to Flight Dojo for part 2 of our series on the Napier Sabre engine. Originally this series was going to be a single part, and when I made it I did not expect the massive amount of views that this series has ended up getting. That being said, I expected a very small amount, and if you haven't noticed, this is by far the largest video on this channel. As such, I think that it deserves much more attention and better research to support my claim that the Sabre was the ultimate World War II aircraft engine. First off, right off the bat, before we get started, let's address something. Many of you commented on the first video in the series and discussed the horrible pronunciation of Napier throughout the video. And on one hand, at first, I was pretty embarrassed by this. I usually don't mispronounce things, and I do apologize. I did butcher it quite a few times throughout that video. On the other hand, I think the number of people who commented on the video and discussed my horrible pronunciation ended up driving the algorithm for many more people to watch the video. So, on that hand, thank you. For those of you who tuned in to correct me, I think you overall helped the video, and it leaves me wondering about whether I should intentionally mispronounce things in the future, but that is neither here nor there. So just to set the record straight, it's pronounced Napier, like rapier. Now there are a few of you that say that I should be saying it Napier, which I think is probably also a good pronunciation, but for the sake of this video, we're going to go ahead and pronounce it Napier. When I move quickly and I talk quickly, I had a tendency for my Midwestern accent to kind of come forth, and I was saying Napier, like I'm going to put a Napier in my John Deere. So I do apologize for that, like I said, but we're going to call it Napier and move on. So let's clarify what I mean when I say ultimate World War II aviation engine. Now, many of you commented on the video, the first part, discussing things like the reliability of the Sabre and its teething issues as it was developed throughout the war. And I do think that those topics have merit, and those things we will discuss as we go out through this video. But I'm predominantly talking about the total power output of that engine. If I, all things aside, as far as reliability and those other things, had to pick a single engine to power my aircraft, I think based on the data that we're going to review here today, the Sabre would be the best choice for your aircraft from 1940 to 1945. That is specifically before VE Day. So these aircraft engines are seeing service in the war. I'm also going to correct some things that we got wrong on the first video about the service dates of some of these engines. I do have a new source. For those of you who are paying close attention, the source that I'm going to be using for all of the data in the second part of the video is Allied Aircraft Piston Engines of World War II by Graham White. In the first video, I was using many articles that I could find by other journalists that had written them in the past, and it was difficult to find a good, accurate source for information. And so to remedy that issue, in the second part, I have gone and purchased many books on the subject, and this one seems to be the best in my opinion for this particular subject. And so it is going to be what I use predominantly to refer to the technical data. So let's start by talking about a few of the things that were brought up in the comment section of the first part, namely ones that discuss the reliability of the Sabre. Now, the Sabre did have reliability issues, but to set the record straight, many of these reliability issues were not related to the high speed of the engine, as some of you pointed out. Many people stated that the high 4,000 RPM operating speed of this engine, the many moving parts, were contributing factors to the reason why the reliability was poor. In fact, this couldn't be further from the truth. As Graham states in his book, the prop production gearing of the Sabre was one of the most innovative aspects of its design. In fact, it completely remedied some of the issues that other high-speed, reduction-geared aircraft engines had suffered from previously. Now, for brevity's sake, I don't want to get too technical in this video. I don't want to talk about all of the specific components that contribute to some of these design elements that I'm discussing, but just know that this book does do that. We could talk about how, each crankshaft drove a pair of straight-cut first-stage pinion gears, which integrated with a second-stage pinion driving the reduction gear. These second-stage pinion gears featured a helix angle, which generated an end-thrust as power was transmitted. The upper and lower pinions were connected with a essentially pivoted balance beam, and preload volute springs acted on the ends of the beam against the pinions, thus ensuring that the helically cut pinions would float along their longitudinal axis as they transmitted the considerable power of the Sabre, guaranteeing equal tooth loading, right? So I could go on and on throughout the video quoting my source concerning specifically, technically, how these problems were solved, but I think that's going to be a little bit too much detail for this video. So mainly, when we're talking about the prop reduction gearing, the main point that we should get across with Napier's design here and why it was so revolutionary was that they solved this equal tooth loading problem. Essentially, when you were applying a lot of force to these reduction gears, there was an issue where the torsion was not being equally applied to each tooth on the reduction gear set. So they found an ingenious solution to this problem, and therefore it was not a problem for the engine. So I'm including this because it's important for me to say that, like I said, we're going to get into some of the stuff that contributed to the reliability issues of the engine, but the speed of the engine, that higher RPM in which it's using to achieve much of its power, that was not the issue. That was not why it was having issues. Another issue that was brought up was the Kaufman starter. So the Sabre started using a shotgun shell. Because the electric starters in England at the time of the Sabre's manufacture were not powerful enough to turn it over and start it, they needed to find another way to start the engine. And the way that they accomplished that was with this Kaufman starter. Essentially, instead of using an electric motor to turn the engine over for start, we're having to use this 25 horsepower shotgun shell, fire it into the engine, and that turns the engine over. Now, unlike an electric starter, the shotgun shell method, this Kaufman cartridge starter, has a vicious acceleration on that engine. It spins up quite quickly in comparison to a conventional starter, which has some interesting issues. The first is because that acceleration is so vicious, if we're not well lubricated, our sleeve valves aren't well lubricated, then it can cause horrible damage to the engine very rapidly. Because of this, and to combat it, there was actually a separate auxiliary fuel tank in the wheel well of the Tempests, I think, and the Typhoons, that had a 70-30, almost like a two-stroke oil-gas mixture that they used for priming the engine upon start to help alleviate some of these problems with the sleeve valves not having adequate lubrication prior to start. Also, this Kaufman cartridge system also is probably responsible for the fears around the Sabre's starting procedure in general. Because overpriming was also an issue, you could have sleeve valve hydraulic lock, which could result in engine fires, and that's why so many people were terrified of starting this engine, because it was very, everything about this engine was very tightly toleranced. This is essentially a racing engine that's being used in hot, dusty, wartime conditions. So, if you don't get everything just right with this racing engine, then things go wrong, and they were very much experiencing this. So I think when we're talking about the reputation of the Sabre in terms of reliability, we need to separate out the starting system from the engine's design. The starter had some quirks, and it did not contribute well to the reputation of the engine early on. I don't think that it's fair to count it against the Sabre in terms of the Sabre's reliability, when the only starter that they could come up with in England at the time, due to the wartime restrictions, was this Kaufman starter system. If they would have had electric starters, similar to the ones being used and employed on aircraft engines in the United States, for example, all of this reputation of being, the squirrely engine to start that causes fires would have probably been alleviated. So I don't think that that is a fair comparison and a fair jab against the Sabre, and that's why I'm bringing it up. So let's get down to the nitty-gritty. Early on, the Sabre absolutely deserved its poor reliability reputation. Its first actual implementation in an aircraft happened when a member of Napier's design staff, A.E. Hagg, designed and put it in the Heston Type 5 air racer to try to recapture for Britain the world's airspeed record. The aircraft took off at 9.2 psi boost at 2,560 rated horsepower at 4,000 RPM, around the same time that the Battle of Britain was taking off. We're talking about June 1940 here. Unfortunately, 7 minutes after takeoff, the Sabre, generating so much power in such a small package, had severe overheating issues and shut down. The pilot conducted an emergency landing and stalled the aircraft 30 feet above the runway. Fortunately, the pilot did survive this mishap, but it was a harbinger of things to come for the Napier Sabre, indicating that some refinement was necessary before the thing could enter production. Interestingly, shortly after this first air racing test and the first design studies, they tried incorporating a contra-rotating propeller with the Sabre in 1941. Unfortunately, as I think this would be awesome, no production Sabre actually used this concept because of issues with suitably designed propellers, and it was decided that they had more pressing issues to resolve. And just another quick non sequitur that I found interesting in some of the research was that a 3-speed 2-stage supercharging system was also developed in 1942 and subsequently not employed or used in any of the Sabres. which would have probably alleviated many of the altitude problems in the implementation of the engines, for example, in the Typhoon and the Tempest. But for reasons that these sources don't point out, like I said, it was never used, which was unfortunate. So if it wasn't really the high RPM of the Sabre that caused these reliability issues, nor was it the Kaufman cartridge that was using to start the engine, what was it? Why does the Sabre have such a poor reputation for reliability even today, as evidenced by some of your comments in the first video? Well, as Mr. Graham White points out in his book, essentially we have to set the stage here. The Napier Sabre, as quoted by White, was the preeminent best design for an aircraft engine ever produced during World War II. He says that himself, and I, as evidenced by these videos I'm making here today, agree with him. Now, that being said, we do need to consider this reliability issue because it is a big elephant in the room. Now, you have to set the scene. This is the most tightly toleranced, high RPM, precisely manufactured engine that has ever hit the production of engine manufacturers at the time. So much so that the early testing engines used to present to the Air Ministry were hand-built, hand-fitted, and carefully assembled by top craftsmen. So when this thing entered production, we're talking about a huge transition between these handcrafted engines and a reproducible production engine. So not only did this engine, raise the bar for what a high-performance engine design could do at the time, but it also raised the bar of what was asked of engine manufacturing at the time. This thing required completely new tools to be manufactured. It was also more complicated than any other engine at the time. So what you see as this thing enters production is there are huge issues between these very, very fine tolerances of the sleeves as well as the sleeve drives, which you can refer back to part 1 of the videos if you're not clear what those specifically are. Now, Bristol had already learned the hard way that manufacturing these sleeves was exceptionally difficult, and they had already come up with a way, which we'll talk about in a second, to overcome it. But at the time, Napier didn't know this, and they didn't realize that that point, I think it's 0.1 inches of last-minute grinding between the exterior of the sleeve and the bore of the cylinder, resulted in an out of roundness. Just that much of the last-minute grinding resulted in this out of roundness, which ended up causing sleeve seizure and the loss of compression in a lot of these early engines. And what they do early on to try to combat this is they start silver plating some of these sleeves, which turns out to be kind of a lukewarm solution. Many of the reliability issues aren't really resolved by it, but it does kind of put a Band-Aid on it temporarily. Ultimately, what ends up fixing the issue is when English Electric takes over the project and a man named Rod Banks took over the development phase. And Banks happened to know that the Bristol Taurus shared the same cylinder bore of 5 inches with the Sabre, and he knew that the Bristol had created some of these sleeves for sleeve valve type engines, like the Taurus. So Banks essentially wants to start testing these sleeves in the Sabre, and he does. And he finds out that these reliability issues are hugely alleviated by using this Bristol sleeve. It's made out of a different compound. It's got a lot of these issues resolved. So he asks Bristol Engines to go ahead and manufacture Sabre sleeves because it's 1943 and the Allies are not winning the war. Well, it's not that they're necessarily losing, but in 1943, it's far from won. We really don't know which direction it's going to go. And surprisingly, despite the political and wartime climate, Bristol at first says, no way. Those are confidential sleeves. I don't want to give those designs away. This is proprietary, corporate knowledge. And fortunately, better senses prevailed, and they were eventually impressed upon the gravity of the situation for the Sabre, and they ended up capitulating and manufacturing the sleeves, which was great. And so eventually, we start seeing that these Bristol sleeves are being used with the Sabre, and some of the reliability issues are being fixed, but much to the chagrin of the Napier company, the Sabre is still unreliable. And again, it comes back to Sabre is a complex engine. It's being shipped out to these guys in the squadrons, in the field, and this manufacturing schedule can't keep up. It's very difficult to manufacture these engines. Again, they were hand-tooled to begin with. They have a lot of moving parts. So they end up making it out of the squadron, and we've got issues where we've got cases with poor workmanship, broken piston rings, machine cuttings that have been left inside the engine, and we also have some mechanics that were trying to hot rod these things. So they're adding custom boost settings from the supercharger and causing detonation and engine damage, was not doing good for the reputation of the Sabre. So soon thereafter, we got some court-martials that happen. And after that, actually, the engine, after some of these issues were attended to, it actually became a very reliable engine. So by 1944, we had the Sabre 5, and much of this stuff, this early 41 to 43 kind of stuff, is dealt with. The 44-45 Sabre is a completely different beast than the early Sabre, and much of this reliability that is now kind of still infected the reputation of this engine was dealt with. They had finally learned how to manufacture this very precise instrument. And all of this kind of coincides with the Sabre 5, the fifth iteration of the Sabre. They relocated the supercharger clutches that were previously overhung to behind the crankcase, which is a more conventional inline configuration, which helped some of the mechanics, apparently, as well as the supercharger's two-sided impeller was replaced with a single-sided impeller. As also, the Sabre moved from carburation and to a fuel injection. So all of these things kind of came and coincided with the Sabre 5 and really helped it finally iron out a lot of the kinks that we're discussing here today. And all of this culminates for the Sabre with the Sabre 7, which is quoted as being not only the pinnacle of Sabre development, but the development of production aircraft piston engines. So even Graham White, in his book, states that the Sabre 7 was the pinnacle of development of production aircraft piston engines. So there you have it. Now, again, how much of an authority you want to say Graham White is, I think he is quite a good authority. His book is quite great. If you are interested in these videos, I highly suggest you read the book. But the Sabre 7, it had that 2238 cubic inches, and it made 3,500 horsepower at 3850 RPM at 70.6 inches manifold pressure. Now, a huge thing that needs to be stated about that 3,500 horsepower number is that Sabre 7 with 3,500 horsepower was not using what he calls in this book ADI, which we could call NW50 or whatever you want, but essentially it's anti-detonation injection, water injection, methanol injection, whatever you want to call it. That's not even using any water injection. So we're going to redo a comparison with some of the revised data from the first video with a better source for the dates and horsepower numbers. And I think you'll be very surprised that not only am I believe I'm correct in saying that this is the ultimate World War II aircraft engine, but it's even better than I thought it was. One thing I wanted to touch on before we go to the graphs is one of the comments from the part 1 of this series mentioned that, how could the Sabre be that great of an engine if we didn't see its widespread adoption and use by other countries, such as the United States? And in fact, the United States did look at the Sabre, and they were very interested and impressed by its design, specifically its huge horsepower numbers. But unfortunately, because it was such a different design from what they were manufacturing at the time in the United States, considering the Packard, Merlins, and the Allison engines are all these conventional V-type. None of their engines are using sleeve valves. They just didn't have the tooling, and they didn't have the manufacturing prowess at the time to spin this thing up in the production that would be required from them to implement it in an allied United States aircraft before they expected hostilities to end. So it just was not the right time. So let's take one more look at the data. Now, as some of you pointed out, the engine that I used for comparison for this Napier Sabre in the first video was the E122. Now, I didn't know this at the time because my sources were inadequate at reporting dates of usage and the frequency that these engines were used, but the E122 was not fair to include because it was not built or used in the war. It was built in 1946 as a test bed, and it was never flown. So the E122 was out. Those initial graphs that include those numbers, they don't count. But it's kind of almost irrelevant because the Sabre 7 was just as good. In fact, in some metrics, it was even better. So the fact that the E122 is the one that I used, whereas the 7 was the last that actually entered the war, is irrelevant. One more thing before we do the comparison is I think it's fair to bring up the criticism that I am only using sea-level data. And what I've learned through this research is that many of the forced induction systems of these engines were actually included inside of the crankcase as an integral part of the engine. So it could be argued that the forced induction system is, in this case, just as much a part of the engine as the crank or anything else. And I will grant you that, the forced induction system is hugely important, and it is completely going to shape the way these things are flown and used in their applications based on the altitudes that are required. We look at the Tempest and the Typhoon, and they become low-altitude fighters because the forced induction system of the Sabre, it sucks. And, we look at the research and we know that's because they had a better design, but they had to deal with these teething issues to get this thing out and into the war as fast as possible. So they just never made a better forced induction system. But the other thing, and the other reason I'm not including altitude data, is because it's just such a confounding variable. We can imagine that with a all parts equal forced induction system, we could compare the horsepower values at sea level and get a good idea of how good an engine is, and if we could just get air to it. And the thing is that these different force induction systems create these different curves of loss of horsepower with altitude, and what is the best engine at a certain altitude band may not be the best at another, and so on and so forth. And so the comparison really gets very convoluted if we look at the entire altitude scale as a whole. So, you could cherry pick other engines at specific powers and power to weight ratios at specific altitudes that might have a better, smaller margin between them and the Sabre. I don't have the time for it. To be quite frank with you, that would make this an hour-long video. So we're going to just stick with sea level. And I am keenly aware that the Sabre sucks above 25,000 feet. I don't think that's on the Sabre. I think that that's on the timeline of the war, and we wanted Sabres in the war, and we didn't have the production time or the development time left on the timetable to get it done. So that's where I'll leave that. All right, let's look at the first of 3 charts. Now, the keen eye among you might notice that some of the titles of these engines have changed, and that is because some of the late model variants of some of these engines did not make it into the war. Unfortunately for some of them, that has shaved a few hundred horsepower off of their total numbers, because again, the criteria for this comparison is that the engine variant had to enter World War II. So you'll see here the highest horsepower number I could find for the Merlin was the Merlin 66, clocking it at 1,710 horsepower. I believe I did not change my Allison label, so that variant number could be wrong, but that is the one that was included in the P38L at 1,500 horsepower. Now, there is some people that claim that 1,600 horsepower was the number. 1,500. Ultimately, it's not going to change the ranking of this engine, but 1,600 may have been, but I couldn't find that in print, so I'm using 1,500. For the DB605DC, we're going to still use that same number from the first video. It's 1,973 horsepower, and the Griffin 130 actually did barely squeak in to service. It was used in the Spiteful, the Supermarine Spiteful, and it was first flown in 1944. So I'm counting it because it flew in 1944, but it's coming in at 1,973. Excuse me, correction, 2,420 horsepower for the Griffin. The Sabre 7, in this case, is the one that was implemented on the final variant of the Tempest. It is making 3,500 horsepower at 3,850 RPM at 70.6 inches mercury. And last but not least, we have the Pratt & Whitney R2800. Now, for this comparison, I'm using the Dash 77 at 2,800 horsepower with water injection. That was in the P47 November. There is the Dash 87 that was used in the mic. It makes the same horsepower, so it doesn't really matter. So there's the 77 or the 87. It's the same thing. So let's just talk power to weight, because that's what we really care about. Specific power is, it's the total horsepower divided by the displacement, but that doesn't really help us, as we stated in the first video, when we're putting it in an aircraft. What we really care about is how much power are we cranking out of how much weight we have to take on, okay? So with the Merlin 66, we're at 1.04 power to weight ratio. The Allison here is 1.07. The DB605 is 1.18. The Griffin 130 is 1.22. The Sabre is 1.48. And the Pratt & Whitney is at 1.18. Now, we're not done. It gets much better. So in the second chart, we're kind of evening the playing field a little bit. Now, as I said before, I'm not sure on a couple of these engines, but most of them, except for the Sabre, I'm not sure on a couple, but most of them are using an anti-detonation injection system. So again, water injection, methanol, water injection, whatever you want to call it. They're using an injection to delay the onset of detonation so they can run higher manifold pressures before detonation becomes a problem. Now, the Sabre at 3,500 horsepower is not using any such system. It was tested, however, during wartime when they were suggesting putting an ADI system on the Tempest, but it never came to fruition. However, whether you call this cheating or not, there was a test stand Sabre 7 that was slotted to be put in a Tempest inside of the parameters of World War II that made 4,000 horsepower with water injection. Now, the R2800 is using water injection in the field in P47s to make its 2,800 horsepower number. The Merlin 66, similarly, to make 1,710 horsepower, is using water injection, and so on and so forth. As we know, the 1973 horsepower number from the DB605 is using MW50. So if we even the playing field and we give a Sabre 7 a water injection system like its predecessors, like its peers, I shouldn't say predecessors, like its contemporaries, it makes 4,000 horsepower. 4,000 horsepower at its 2,360 pound weight, right? So gives it a ultimate power to weight ratio of 1.69. 1.69. So in this graph, it is at its 1.69 number. It is dominating every other engine in its class. But it gets even better. So I'm not even including the numbers that I can't get for the Sabre after weight was reduced. That's right. For every calculation in this video, I'm clocking the Sabre at 2,360 pounds. And that is from a Saber 2's weight. A Saber 2A, I believe, is 2,360 pounds. Now, I know from this source that from Saber 5 onward, which would include Saber 7, that there were 12 first-order counterweights on the crankshafts that were removed because it was discovered that the engine ran just fine, smooth enough, without any of those counterweights in the engine. So I don't really know how much they weigh, each individual counterweight, but 12 of them were removed from the engine. So I don't know what that does to the weight, but it's less than the number I'm using. So I'm making 4,000 horsepower with a 1.69 power to weight ratio, and I venture to guess that probably a couple hundred pounds I could shave off the weight, and I'm not even doing that in this graph. One last thing I wanted to touch on before the end of this video was that some people included the idea that an air-cooled engine is not a fair comparison to a water-cooled engine because the weight of the additional cooling components, such as a radiator in a liquid-cooled engine, is going to reduce its power-to-weight ratio if you were to include them. So we're assuming the Saber 7 in this case at 2,360 pounds does not include the weight of its radiator, the chin radiator underneath the Tempest, for example. Whereas the Pratt & Whitney, making 2,800 horsepower at 2,360 pounds, is including its complete cooling system along with it. Now, the answer is I don't know how much a radiator weighs for the Saber engine. That chin radiator, I can't tell you how much it weighs. There's no data to support that number. But I did make you a graph assuming that it weighed 400 pounds. I don't think it weighed that much, but let's assume it did. At 2,760 weight, and I'm including the 12 counterweights, which we know aren't in the engine. I'm including those 12 counterweights, and I'm giving the Saber 7 a penalty of 400 pounds to include its radiator. Now, it might be more than that, but I would be very surprised. With those penalties, at 2,760 pounds, the Saber 7 is dominating the Pratt & Whitney 2800. It's just not even close. So I think the argument, even if I'm padding the numbers to penalize the Saber for not having its cooling system included in its metrics, it's still winning. So I think that argument is kind of put to rest unless somebody can get better data. So if you've made it this far, I really want to thank you for tuning in for part 2 of my series on the Napier Sabre and why I believe that it's the ultimate World War II aircraft engine, as apparently does Graham White, as he said that it is the pinnacle of engine design during the war. I'm going to be doing more of engine videos. I'm going to be including an engine video, I believe, on the Merlin, the Allison, and I think the next one's going to be on the Pratt & Whitney R2800. That is the top request that I have received. So once again, thank you guys for tuning in. I really do enjoy making these videos for you, and I thank you so much for the support, and especially just the algorithmic help that we've gotten recently for the channel. So I'm very excited to keep making content for you. Please don't forget to like and subscribe, and feel free to have some discourse with me in the comments. I do love your guys' input, especially your stories and personal connections to some of these engines. So feel free to do any of that, and once again, I'll see you guys next time. Thanks.